Alrighty, welcome and hello. This is a lecture on HEC RAS, Lecture 2, Bridges, Inline Structures, and Comparing Plans. So if you haven't used HEC RAS before, you're in a good place. Lecture 1 was yesterday. I'll leave a link to that in the chat and also in the description. If you're watching live, I have the live chat open, so I have that on my other screen. There was lots of good chat yesterday, and happy to have you along today if you're back. This is lecture 2. You don't have to have done lecture 1. These are considered drop-in lectures. So if I bring up the Bosch Solutions webpage right here on the screen, the URL in my email is on the bottom of the screen right now. But if you click on this top right link, services, we're going to actually start today's lecture by downloading some starting files. So you don't have to have done any of the previous lectures. I'll hopefully explain everything in enough detail. And if not, go ahead and leave me a comment or a chat. All right. So if you go to this Bosch Solutions webpage and then click on the services link in the top right corner, and then scroll down a little bit, we have this water modeling drop-in lectures. That's what we're talking about here. I'll move the label. And you can see the schedule of upcoming lectures. We have lecture 2 that's happening now, lecture 3 that's tomorrow, lecture 4. I do want to point out that it's actually lecture 4 is at an hour later than normal because I have something to do. But anyway, uh, if you happen to be visiting this web page and looking for the starting files at a time where there's no upcoming lectures, you can click on this link right here to download lecture files and then just download whatever files that you're using for that particular lecture. Okay, the Excel files have all the lectures for both RAS, ResSim, and I'm sure I'll get some HMS lessons lectures and data files up here soon enough. Okay, so let's go ahead and if you're following along, just do a single left click on the Excel data file and then also a single left click on the starting project files, this zip icon. We're going to need both of these to get started if you're going to follow along with me. And if you wanted to just watch for fun, you're welcome to do that as well. All right, so those downloaded to my desktop. So let me go ahead and just switch views here. Here is my HEC RAS, and then the files that I downloaded are right here. So I've got a couple of desktop icons. I'm going to open up the Excel file first and then just see what we got. After that, we'll open up the zip file. Okay, so here is the Excel file contents, and let me just get that into view here. Along the bottom, I have a number of different worksheets, L1, L2, L3, and so on. L2 is the data for lecture 2, so this is the data that we're going to be using a little bit later in this lecture. So just go ahead and kind of keep that on hand, but for now, I'm just going to move it over to the side. And then the other file that we downloaded is this lecture 2 startup.zip file. And in here we have some starting files. So I'm just going to go right click and copy. And then I'm going to move this to a location on my computer where I want to store those files. So I have a directory that's all set up right here, right click and paste. Boom, they're ready to go. So I can move that out of the way. And now I can delete that zip file. And then for the Excel file icon, I'm just going to kind of move that out of the way. All right. So if I'm going too fast, you're welcome to obviously pause the video. If I'm going too slow, you can scrub ahead or watch me at double speed. That's what I usually do. And I wouldn't even know. So let's go ahead and get started with this exercise. Oops, excuse me. This lecture. I'm going to go back to Bosch real quick and just read the description of what we're doing here. Okay. So it says, in this lecture, we'll continue with 1D steady flow example by adding a tributary reach and updating the flow file and then running the model. After that, we'll create two geometries. One will include a bridge. The other will include an inline structure. We're going to then run the simulation and then compare the results. So that's kind of the general direction we're going with this lecture. All right, so up here in the main HEC RAS interface, I'm going to start by just going File and then Open Project. I'm going to navigate to that project directory where I saved those files from the zip file folder. So for me, that was in lecture 2. I put them right here, I believe. Click on lecture 2 and then click OK to open. All right. So what we have here is our file GUI, and then down below here in the geometric data editor, we have a river reach. This is actually the ending point of lecture 1, if you were with me yesterday. where we have a river reach. It's 1,000 feet long. It's a single river, single reach, and then our cross sections are just uniformly distributed every 100 feet from river station 0 up to river station 1,000. All right, so as I mentioned, we're going to sort of divide this lecture into two parts. First, it's going to be examining tributary flow and diversions, and then the second part is actually going to be what the title says, bridges, inline structures. So I should probably modify that video title to include this first part of tributary flow. Alrighty, so I'm going to add a tributary at river station 350, and then we're going to modify the flows to see, or the flow file to see what that looks like. So river station 350 is right here. Here's 400, here's 350, and I'm going to just zoom out a little bit. Pan. If you need a pan, you can hold down the shift key. That gives your cursor the pan hand, and then a single left click to drag will help you move the display around this geometric data window. And then what I'm going to do is click on River Reach. So, and then single left click, sketch from upstream to downstream. So with the River Reach tool selected, I want it to end at 350, but I'm going to start it further upstream, maybe over here. So we'll just do like a single left click, single left click, single left click, and then I'm going to zoom in. Oops, pan. Okay, and then just try to get it as close to 350 as possible, which is probably around here. You're going to want to double click to terminate the reach. And then, okay, cool. So it looks like we're good. Now what it's asking me is for a river and a reach name that's associated with this tributary. So for the river, I'll just call it Trib A, and then the reach one is fine. So I'll just click OK. All right, it's going to ask me a few more questions now. The next one is, do I want to split reach the existing river, reach one, and at below node 400, so specifically at 350? And I want to say yes. So the existing river was called River A Reach 1, and it's still called that upstream of this, what will be a junction. But downstream, it's now asking me, what do I want to name the river? And the answer is I'll call it River A, but I'll call it Reach 2 instead. So River A is going to have a Reach 1 and a Reach 2. And then this is the last question. It's asking me uh, what the junction should be called. And I'm just going to call it J350. Oops, 350, just representing the river station of 350. Okay, so we are all set. We have our tributary, our junction, and now our river reach here is the in two parts now. The river A is now a reach 1 and a reach 2, and we can confirm that if we go to the cross-section data button over here on the left. We have our river A and we have our trib A. River A now has a reach 1 and a reach 2. Reach 1 ranges from cross-section 1,000 down to 400, and then reach 2, the downstream end, downstream of that junction, has cross-sections at river station 300 down to 0. All right, so what we need to do now is add some cross-section data for our tributary. So to do that, one best practice is to actually match the inverts so that the downstream most cross-section of the tributary has the same invert at this junction point as this river A does. So what I'm going to do is just split the difference between cross-sections 300 and 400. Let's bring up that geometric data editor once again. Oops. Okay, cross-section data. There we go. And I'm going to look up what sort of data we have for the inverts. So at river station 300, it's 32.6. And then if I look at the cross-section at river station 400, I need to switch to reach 1. And then 400 is this one, 32.8. So the average between 32.6 and 32.8 is going to be our 32.7. That's the invert that we want to use for our tributary. Oops. Right down here, at the very at its confluence with the junction and river 1. All right, so to do that, we're going to click on Options, Add New Cross Section, and hold on a second. What I want to do is first select Tributary, and then yeah, Reach 1. It's the only reach in the tributary river, and then it's highlighted over here. But what I want to do is again, click on Options and then Add New Cross Section. Okay, so now it's asking me where in this tributary river do I want this new cross section to be located. I'm going to say river station 0, which represents the downstream most reach, downstream point of that river, and then click OK. All right, now I want to enter the station and elevation data of that cross section, but I want it to be, I want to make sure that the invert is, what did I say, 32.7. So if you still have that Excel data that we downloaded at the beginning of the lecture, and in the Excel file, if you click on that L2 worksheet at the bottom, right here in this first table of data in columns 2 and 3, this is going to be our cross-section data for the tributary at River Station 0. So I'm just going to highlight those values, click Control C to copy them onto my clipboard, and then back over here in the cross-section data editor, highlight those fields, Control V to copy, and then boom, I'm good. So that's in place. I'm going to add a few more values here just to finish off the cross-section data. So I'll say the leftover bank value is 0.05 and 0.03 for Manning's N. Those are just some standard numbers I use. And then the bank station will be 60 and 150 for left and right. And then I'll click Apply Data. Okay. So over here on the right, I have the preview. If you don't see this preview, you can click this button to toggle it on and off. I like to just always keep it on. And good, we have our cross section down here. We want to add one more cross section at the upstream end. And I'm going to just say it's 500 feet upstream. So our tributary is 500 feet in length. So to do that, you probably already saw this in lecture 1. I'm going to go a little bit quicker, but I'm going to go options and then just copy the current cross section. This is, yeah, trib A, reach 1, but it'll be at River Station 500. And okay. All right, so a few changes I need to make is just change the downstream distance to the next cross section from 0 to 500. Again, we're now editing the cross section at River Station 500. And then the one other thing I need to do is update the elevation. So I need to increase the elevation a little bit. So of course the water flows downstream towards that junction. I'm going to add 0.1 foot. I'm sorry, I'm going to add 1 foot, and then that would be a 0.2% slope because it's a 1 foot change over a 500-foot length. So I'm going to go options and adjust elevation 1. Now when I click OK here, all of my numbers here should increase by 1 foot. Okay, so that looks good. 32.7 is the invert upstream, and then it flows down to 33.7 down to 32.7, and that's going to be at the junction. Okay, so I'm going to click OK, or sorry, apply data, close the cross-section data editor, and now what we have, excuse me, now what we have in our plan view is the upstream and downstream cross-sections for this tributary. And just to finish off this particular geometry, what I'm going to do is add some cross-section data, some intermediate cross-sections every 100 feet, the same way we did for River A. So to do that, I'm going to go Tools, Cross-Section Interpolation, within a reach. Make sure to select Trib A and Reach 1. That's good. And then 100 feet right here. Interpolate and close. All right, so I have my cross-sections that are interpolated from 0 up to 500. All right, so that's all we need to do for our geometry. I'm going to go File and then save the geometry data. And let's go ahead and add some flow data, run the results, run the simulation, view the results, and then move on to bridges and inline structures. So to do that, we're going to go up to the top and click on Edit, Steady Flow Data. Now, what I have here is sort of leftover from the previous exercise, the previous lecture, where I had two different flow profiles, a 10-year and a 100-year. I'm going to just use one flow profile here and remove this second one. So at the top, I'm going to change the 1 to a 2 and then just tab off. It's asking me, am I sure I'm going to lose that data? Yes, that's true. And then that second column has been removed. Okay, so what we're doing here is we have 400 CFS that's starting at this upstream end of River A at River Station 1000. And then I'm going to say that the tributary at River Station 500 right here contributes 300 CFS of flow. Hey, Kadir, good to see you again. Go ahead and leave any questions or comments in the chat. I'll address them as soon as they come in. If they're really off topic, I may ask to wait to the end of the video and to address them. So just yeah, welcome to the chat. 300 plus 400 is 700. So I'm just going to say there's conservation of mass and volume and momentum and all that so that we have 700 of CFS of flow from the junction to the downstream end of this river A through reach 2. All right, so this is all I'm going to do for my flow data. I'm going to go File and then Save Flow Data. Let's go ahead and run this simulation now. So I'm going to go up to Run, Steady Flow Analysis. We're still doing steady flow, and it's still going to be subcritical. All of the changes we made to the geometry base file and the steady flow base file, which is what we were editing, are already saved here. So all I should have to do is click on this Compute button, and then it should run. Okay, so that looks successful. I'm going to click close down here in the bottom right corner. And then we can look at some of our results. I'm going to go up to view and then cross-section data. So over here in the plan view, the geometric data editor, you can see highlighted in magenta, sorry, is the cross-section that is showing up in this view here. So if I scroll down, 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 you can see the magenta cross-section is getting updated at the same time we're seeing results for that particular cross-section. So this is not particularly exciting because one, it's steady flow, and two, all of the cross sections have basically the same shape. They're just decreasing 0.2% slope as we traverse downstream. So we can look at the different cross sections for River A as well, both in Reach 1 and Reach 2. Here it is. This is, I believe, 400 CFS of flow. So we can see that. And then downstream of the junction is Reach 2, where we have a flow of 700 CFS. And again, this is subcritical. I'm almost positive. Let me go ahead and toggle on a couple of variables. So we can toggle on the critical depth and the energy grade line. Okay. And since this water surface elevation is above the critical depth, I'm just scrolling in with my mouse button. This is the critical depth right here, the red dash line. Here's the water surface elevation, the blue line. We know for sure that this is indeed subcritical. This green line here is the energy grade line. All right. Well, that is it for diversions. Split flow is similar. So split flow is basically if we remove this tributary that was flowing into the river, and split flow would be, for instance, if I sketched another river that starts at the river A, and then it flows away from river A, meaning the flow in river A can continue in river A, or it can be diverted through a split flow scenario. It's less likely in nature that there's split flows. Typically, there's diversions. Is a lot more common, but split flows do happen. Okay, sometimes within the same river too, and then it reconverges a little bit further downstream. But I can demonstrate that briefly. In the geometry here, I'm going to just delete what I already have done so far in this lesson. So I'm going to go up to Edit, Delete. First, delete the reach before the junction. So if I click Reaches, then I can select the reach I want to delete. I'm sorry, the river first, and then the reach. Just double click so it's over here. Click OK. Am I sure? Yes. And then boom, that tributary is gone. I'm now ready to start sketching my split flow. Now, I haven't actually deleted the junction yet. See, it still says J350 right here, which means that the station data, like my river is still divided into one, a, a reach 1 and a reach 2. If I click on cross-section data, I can confirm that because we have river A and then we have reach 1 and reach 2, where reach 1 again is just from 1,000 down to 400, and then reach 2 is from 300 down to 0. All right, so if I want to remove the junction, then that would just give me one single reach 1 again, I believe. So let's go ahead and just do that. So I'm going to close the cross-section data editor, come up to Edit, Delete, Junctions. This is my one and only junction here, so move that over. Okay, I'm sure. And then let's check out the cross-section data. And now reach 1 is my only reach, and now we have all 11 cross-sections listed right here. All right, very cool. That's what I expected to happen. Anyway, if we wanted to sketch out a split flow, I'll just do that briefly, and then we'll move on to bridges and inline structures. What we do is click on this river reach tool once again, and then instead of sketching a river that flows into our river and converges at a junction, what we do is start at the river and then start sketching away and then double click, name it whatever we want, diversion, reach one, whatever. I'm not going to do that, but just so you know, that's basically the same process as you just saw with the tributary flow. Okay, so let's go ahead and move on to the second half of this lecture. We may go a little bit long because this is only supposed to be 30 minutes and I'm 20 minutes in already. The first time I did this lecture, it took me 50 minutes, so I'm going to try to keep it a little bit shorter than that, but my apologies already. Real quick, I'm going to just run the model so that it will run with, 1 second. I just want to remove this data. So this, remove the row from table and then save the flow data. And then I'm going to run the steady flow simulation. So I don't have to run the base model again. I can just go straight to the bridge. Okay, so that's run. The results are saved. Let's go ahead and build ourselves our first bridge. All right. I got a chat here from Abid Ali, and thank you. I'm using version 6.6 ResSim. I mean, sorry, Heck RAS. I was doing ResSim last week. This is 6.6. 6.7 is available, so you can download that. I think they're on like beta version 3 at the time of this recording, but I assume version 6.7 will be out in its installable form a little bit later. So yeah, good question. The exercises and the lecture I'm doing right here can be run in pretty much any HEC RAS. This is pretty simple, nothing cutting edge at the moment. All right. All right. So I'm going to go ahead and sketch a bridge now. Let's go ahead and add our bridge to River Station 250. So if I zoom in here, here is my stationing 100, 200, 300, 400. 250 would be right here between 200 and 300. And it's going to be centered at 250, which means if I have, say, for instance, a 40-foot wide bridge that crosses the river here, then the actual upstream and downstream most river station for that bridge would be 270 to 230. So the difference there is 40 feet, and it would be centered again on 250. So let's click this bridge slash culvert button over here in the left. And then I'm going to move that over to the side. Here, I'm going to move this display over here a little bit. Ooh, all right. And then, sorry. Okay. There we go. Can we see that? Cool. First step is to come up to options, add a bridge or culvert. And now what it's asking for is the river station number. I'm going to type in 270. Even though it's centered at 250, what it's really asking for here is the upstream edge river station. All right, so now I have in the preview the cross section for upstream and downstream. The next step is to click on this deck slash roadway. And then we have another dialog box here to fill out. So this is where we're going to define the station, high chord, and low chord, both for upstream and downstream. And we'll see what that looks like when we actually click OK, and we'll see a preview of the road, the deck slash roadway over here in the right dialog box. This distance value right here is going to be the distance from the upstream edge of the bridge, the river station 270, to the next upstream cross section, which is in our case 300. So I'm going to just type in 30 because 270 from 300 is 30. And then the width here is the width of our bridge, which is 40 feet. I'm using English units for this project. And then weir coefficient, I'll just go ahead and leave that as it is. Next, what I want to do is specify the station, high chord, and low chord data. So I'm going to start by just typing in 0 and 210, which would be the entire width, or sorry, length of the bridge. And then for the high chord, I'm just kind of looking at my numbers over here, and I'm just going to say 49 down to 46. Now, it would probably be much larger than that in reality, but I'm just going to make something that kind of looks good for the display. So 49 and 46, and then at the other end, the same thing, 49 and 46. And then I'm going to click on this button, copy the upstream data to downstream. So that's just going to copy the data in these columns into these columns to save me a few clicks. So you can do that. I'm just going to set some generic 3:1 side slope and then click OK. All right. Now you notice it did not update over here, but if You may just have to move it. Yeah, see, all I have to do is move this interface and then it will update. We see this gray shading representing the bridge deck. So this is our bridge right here. Also, if moving it doesn't work, you may need to just resize this window and it should update just the same. All right. So very cool. Um, That's what I'm going to do is add a few piers, and then after that we'll move on to defining the inline structure. To define a pier, I'm going to click on the pier button right here, and then I'm going to say that the center line station is um, let's go with 50 first. So what that means is right here at 50, we're going to have a pier. I'm going to add a second pier to the midspan at 105, and then a third and final pier to the right overbank at 160. So we have left overbank, main channel, and right overbank for our three piers. I'm doing the left overbank right here at station 50 first. And then here I need to define the pier geometry. So if you have the Excel file, I'm actually just freehanding this, but we have the data for the bridge right here, and then the data for the pier right here. So we're going to go with a 5-foot wide pier from 0 up to 46 feet. 0 is just an arbitrarily small number that's below the soil surface, and then 46 is the elevation of the low chord of the bridge deck. So remember that bridge deck was from 46 up to 49, and we're just going to go with the 46. So again, 5 foot, 5 foot. The elevation is going to be from 0 up to 46, and then we're going to use the exact same data for the downstream here, but we can be lazy and just click on this copy upstream to downstream. It copies in right there, and then if I click OK, it should update, but let me just grab the display. Okay, yeah, so this is Java. Now there is our pier that's been loaded in. All right, very cool. So I'm gonna make a second and third pier real quick. It's faster than the first one because all we need to do is copy and then update the station number and it should work. So again, I'm gonna click on pier. That was our pier number 1. If we want to add a second pier, we can just we can click add or click copy. And when I click copy, it didn't do anything. Copy. Okay, there we go. So here's my second pier. I'm going to keep this data all the same. I'm just going to change this to 105, which is midspan for the main channel, the second middle pier right here. And then I'll click OK. And then there it is in the display. So that one just loaded in for me right away. And one more time, I'll just click on copy. Okay, now we're editing pier number 3. And then I'm going to change this to 160. And then OK. All right, so we have our 3 piers in place. This is all we need to do for our bridge geometry. In fact, I haven't even created a new geometry file here. So we're good here. I'm going to go ahead and close this dialog box. You can see our bridge is now here. Before I forget, I need to go File and then save the geometry data as. Instead of base, I'm going to call this bridge. Okay, and then that is good to go. Okay. You can see down here in our plan view, this is the schematic of the bridge. It looks kind of dorky and cartoonish, but this is the bridge. So the water is going to be flowing downstream, and then here is the bridge that's centered at station 250, with, of course, the upstream face at 270, downstream face at 230. All right. So I'm going to go File, save the geometry. I think I already did that. Next, what I want to do is create a geometry for an inline structure. So an inline structure could be thought of as like a dam with a weir, dam with a gate, dam with a culvert, but it's going to have a lot of the same or similar editing features that we saw when we created this bridge. So if I go up to File and then Open Geometry Data, we now have Base and we have Bridge. So if I click on Base and then click Open, oops, so this dialog box is a little bit wide, but yeah, in the bottom right, there's this Open button. Boom. It opens me up to the base geometry. If I wanted to open the bridge geometry, click bridge, and then boom, there's the same thing except with the added bridge. Now what I'm going to do is create one more geometry file, create an inline structure, and then we'll go ahead and run a simulation and show how the water surface profile changes for a steady flow 1D simulation for these 3 different geometries. Okay, so I'm going to go up to, let's just open up the base geometry and then save as from there so I don't have to delete the bridge. But either way, it's fine. So I'm going to go File, save geometry data as. This is probably a better way to do it, where you actually save the geometry first with its new file name and then build it, as opposed to what I did with bridge. But I'm going to type in inline structure and then click OK. All right. As with the bridge, I'm also going to put the inline structure at river station 250, which is right here. So instead of bridge slash culvert over here in the left menu, next down is inline structure. So click on that. All right. And of course, it recenters my view, but boom, this is where we're going to be working right here. And okay, never mind. Options, add inline structure. This is the same 270 number that we typed in before with the bridge. And now we want to click on weir slash embankment. Now we have a few different editing tools with inline structures. So we have gates. We didn't see that with bridge. Culverts, we did see that with bridge. We're not going to be going into gates or culverts with this particular lecture. There's plenty of other lectures to come and other videos on the other HEC RAS playlist on this YouTube channel, which you can visit anytime you want and learn about those topics. But anyway, being the very first lecture, lecture 2 on inline structure, I'm going to click weir and embankment. And now I need to define some of the same parameters we saw before. So the distance to the next upstream cross section is 30 feet away. The width of this inline structure, I'm going to go ahead and just call it 40. Maybe that's too wide in reality, but I wanted to keep it consistent with what we put for our bridge structure in the other geometry file. And then right here for our station elevation data, we're going to go ahead and set it to whatever we want, really. We could just say maybe it goes across the main channel here at elevation of, say, 39. So for the station, I'm just going to be conservative and just say it's the entire width. And then the elevation, I'll just say it's a fixed 39 feet the entire way. For a side slope, I'll just say 3 to 1 and then click OK. And then boom, you see this gray shading here now represents the inline structure, or you could think of it as a dam. It's 40 feet wide. It's at river station 270 to 230. And this is just sort of the profile view. We're looking at it straight on in the downstream direction. If you don't see this gray shading pop up, again, you may need to just kind of like move or resize your window, and then it'll refresh appropriately. But what I want to do is add a weir, like a little notch in the top here to demonstrate how that works. So let's go back to our weir slash embankment button. And then for the, I'm going to add a few different data points in the geometry. So I'm going to select this second row, and then I can click this insert button 2, 3, 4 times. And I'm just going to type in some numbers to give me a little notch right here. It's going to, again, be centered at 105 and 20 feet wide, so 95. And then 105, I'm sorry, 115. And then it's going to go from 39 down to 36, so just 3 feet deep, back up to 39. So if I click OK, boom, what we have is a notch right here. It looks like it's equal height and depth, but it's actually only 3 feet deep and 20 feet wide because the scale of horizontal versus vertical is not the same. But just keep in mind the numbers are correct. The display just may look a little distorted. But what we're going to have here when we actually run the simulation is the flow is going to, of course, flow through this notch first. And if the water, the flow rate is high enough, it's going to overtop the inline structure. And if it's even higher still, it's going to overtop the main channel and go into the left and right overbanks. All right. So let's, yeah, that's all we need to do for defining the inline structure. I'm going to close this dialog box, go File, Save Geometry Data. I'm going to check out what we have for flow data. I believe it's just our constant 400 CFS. So that looks good. No need to make any changes there. It's called base. So for all 3 of our plans, we're going to use this same base flow file, but we're going to be using different geometry files. We're going to have 3 plans, one for each of the geometries, base, bridge, and inline structure. So let's go ahead and do that now. I'm going to go up to run and then steady flow analysis. Okay, here we go. And what I already have defined is, okay, so here are my 3 geometries, and here's my one and only flow file. I'm going to first select base, and then I'm going to call this save plan, and I'm going to call it base. I already have that right here, so it's probably just going to ask me to confirm I want to override, and the answer is yes. Yep, that's that question right there. It's asking me for my short ID. I'll just use the word base again, and then I'll go ahead and run that simulation. Okay, so this part's a little bit redundant, but what I just did, I'm going to have to do two more times here for the other two geometries. So geometry file bridge this time, file save plan as, and then I'm going to type in bridge. I'm going to copy that to my clipboard because I know it's going to ask me for that short ID. Boom, here it is. We'll just call it bridge here. So we have bridge, 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 and base and compute. So it's running the simulation. It's done, thank goodness, because it's only a 1D steady flow simulation, nothing too exciting, and nothing too computationally expensive either. And it's saving the results. So we have to do this one more time. File, save plan as. This is now going to be the inline structure. Okay. I'm going to save that to my clipboard. Okay. And then I'm going to name the short ID the same thing. Okay. Subcritical flow. That looks good. So everything's good. I'll click compute here. Okay. So that's done. I can click on close. Now let's go ahead and take a look at those results and then call it good. So to look at the 1D steady flow results or any 1D results, we can go up to the view menu, cross sections. Here is the cross section of the inline structure with the flow in it. So let me just move that over. Okay, interesting. That's probably because I left this geometry selected. It's just why it's the default. Let me go ahead and change something real quick. I'm going to go File, New, Open Geometry. I'm going to open up the base geometry file and then click OK. Oops. Okay, so this is the base geometry with no bridge and no inline structure. And okay, so that's fine. Now let me go ahead and go to the top and then view cross section. Okay, yeah, so whichever the active geometry is what we're going to be seeing here. And the sorry, the plan that I'm looking at is the inline structure plan. So I can, let's go ahead and do a few things. I'm going to toggle off the variables. So options, variables. There's a few variables here I don't really need because I want to look at different plans, not variables. Critical depth and energy grade, I'm going to just say okay, I don't need that. And now I'm going to toggle on the different plans. So I'm going to go up to options, plans. We're going to compare the base plan, the bridge plan, and the inline structure plan by, oops, sorry about that, by checking them all on right here and then click OK. All right, very cool. So this is what I expected to see. There's a very small difference between the water surface elevation at River Station 1000 between the base and the bridge. You can tell these are basically the exact same water surface elevation. So what, 750 feet upstream of the bridge, we have a very minor difference. However, if we zoom out, we can see the the inline structure water surface elevation is way up here at like 39 and a half. So that's, gosh, like 36 and a half. So that's like 3 feet difference. There's a larger difference between the base water surface elevation and the bridge water surface elevation closer to the bridge, specifically at River Station 300. So I'm going to change the River Station cross section to 300. And I mean, it's still fairly severe where the water surface elevation at the inline structure is still much higher than the other two plans with the bridge and base. But if I zoom in here, and then pan up, you can see that there's a little bit more difference between the water surface elevation for the base plan and the bridge plan with our constant 400 CFS. If we actually want to look at some numbers, we can do that as well. So I'll go up to view and then profile summary table. Now what we have here is the far left column shows us the river reach is reach 1, river stationing, and then it's all the same profile, and then our 3 different plans for base, bridge, and inline structure. So these first 3 rows here represent the river station 1000. The next 3 rows down here represent river station 900, 800, 700, and so on. It goes down to 0. That's the last 3 rows. And then for each of these um, river stations, we have, scroll up, we have the three different profiles. So it has the same invert, of course, but what's different is the water surface elevation. Let me scroll down to that River Station 300 right here, which is what we were looking at. So they all have the same invert, of course, but the inline structure has a water surface elevation of 39.5. However, the other two, the base and the bridge, are down to 35.31 and 35.40. So it's about a 4 foot elevation change when we have that inline structure compared to the base and the bridge. The bridge, of course, increases the water surface elevation, but just barely by 0.13 feet. So, like, what is that, 2 inches? Not much, but still, it's something. And the inline structure, of course, by a lot more. All of the flows, of course, are subcritical, hence the Froude number is less than 1. And you can look at all the other numbers here. I just wanted to focus on water surface elevation for this particular lecture. All right, we're 10 minutes over. I want to just show one more result, and then we'll call this good. I'm going to close this. Oops, close the geometric data editor as well. I'm going to go up and to view water surface profile. And now we see sort of the side view of the results here. And specifically, River Station 300 is right here. This is probably the most dramatic. So if we zoom in here, and then highlight the inline structure. This is the water surface elevation caused by the inline structure at River Station 250. And then we have the difference between the bridge and base right here. This is base highlighted, and then this is the water surface elevation due to the bridge plan and the bridge geometry. All right. So that's just another way to view the results graphically, not using numbers per se. But yeah, just wanted to finish up this lecture by saying thanks for joining me. What we did was we added a tributary flow and later looked at a diversion split flow scenario, ran the simulation. And then after that, we created 3 geometries. Of course, we started with the base geometry, but we created a bridge and an inline structure, ran a simulation, a constant, steady 1D flow of 400 CFS, and then looked at those results. All right. Well, I don't see any chat or questions. I'll stick around for another minute. I'm happy to answer questions. If you're watching this, that's already been recorded. You can add comments and I'll see them as they come in after the fact. Okay, we do have something back. Can you bring GIS background into 2D flow? Same area. Do you have flow meter and rain gauge? Do you have flow meter and you can bring in the GIS background imagery by clicking on this button right here in the top right, and then click on plot terrain and click close. However, for this particular project, I do not have any terrain data. I've never used RAS Mapper for this project, but if you have a terrain file that's loaded in, yes, you could just click on plot terrain and then click on close, and then that will show up in your background. And then the other question here is, um, do you have flow meter and a rain gauge? Flow, what I'm doing for this exercise is just assuming a constant 400 CFS. So I don't have any real world data. It's just hypothetical, theoretical data that I'm making up. But in other lectures and exercises, we would have measured data. We can look that data up online. We can measure it ourselves. There's definitely different ways to integrate real world data into these models. All right, yeah, if you have any questions, feel free to write them in the comments. Any of the comments, any of the videos, I'll see them eventually. But I did want to mention that if you wanted to stick around for tomorrow's lecture or anything else later this week, the schedule is on boschsolutions.com. So let me toggle over to the view. I'm going to put up my email and the domain on the screen here, click on services, scroll down, and then this is where we have the water model drop-in lectures. So let me take that off. And then the files for the lectures are right here. If you don't see your lecture here, but yeah, tomorrow will be 1D steady flow and DSS view. And then we'll continue on with a bunch of RAS lectures at the moment. I plan to make more lectures as well as some additional lectures in ResSim and HMS. All right. Well, if there aren't any other questions, thanks for joining me and have a great rest of your day.